Okay, when moments ago I was mentioning that this afternoon we will be starting at 1701, this building, not here. Everybody go to the lab at 2:30. Okay. I hope everybody still remembers something that I said last week. Because you know, you've been being bombarded with too many things in the last 2 weeks. But let me start refreshing that we were talking about steepest descent. That is a simple algorithm. We mentioned two shortcomings. One is usually slow convergence, depend on the function, and then it has good point too. We talked about two different ways to improve them, and we mentioned one of them called expand the subspace, right? So modify let's see, extend a search space. And today we're going to more theoretical than last week, and mainly focus on one particular theorem that I thought is very basic and is helpful later on for preconditioning understanding. So this is what we talked last time. Okay. The extended is basically by noticing the steep descent was basically searching on the Krylov subspace of order 2, and then naturally that we're going to expand space to order m. All right. So this is what we talked about, already covered. Okay, so this theorem we briefly mentioned last week about, this is called so-called global convergence. It doesn't tell you a speed, but guarantee that you will have something out of it. So said for a steep descent or extended steep descent, the rho, which is approximation every step, is going to converge to one of our eigenvalue. We don't know which one in theory, no guarantee. And the residual is actually going to 0. So we know it's going to go to one of our eigenvalue. The proof is not terribly difficult. Here list 4 steps for the easy to understand. First of all, first point is this each approximation, because we're minimizing the function. So every step, the rho L is going to decrease and cannot increase. And yet this rho is always bounded from below by the smallest eigenvalue, because you are searching in the part of the space. And therefore, this rho is going to convert to something. That's basic calculus, that if you have a monotonic decreasing sequences and bounded from below, it can convert it to something. And on the other hand, this each approximate eigenvector, each iteration, we always normalize it. So you stay on, you can say, stay on the bounded set in C sub n, which is, if a bounded set in C sub n is always compact, that means you're going to have a convergent subsequence. So there's a subsequence x, use a subscript n of L, going to go to some vectors. So, so this too, we're going to prove that the residual, then later we'll prove the residual going to go to 0. So the third point would be, this is always true we talk about, because that one of our theorem we talk about, x conjugate transpose Rx is always equal to 0. That's basically because what is Rx is the residual A minus X transpose, conjugate transpose. This is always equal to 0. That is the This is Rx. And so this is always true. This equation is going to be always true because of that. And then if that's true, you can take a limit, and you get x hat, because x, the subsequence goes to x hat, and times r hat, which is the residual, the vector converge, and that's going to be equal to 0. So x hat and r hat are going to be perpendicular. And then what we remain to prove this, this r hat equal to 0. That's because this is going to be converged to r hat. So that's if we can prove r hat equals 0, that's what we need. Using the usual counter argument, suppose r hat's not 0, then x hat, r hat, rank, so put together is an n by 2 matrix. Going to be rank is 2, because these two vectors are orthogonal and not 0. There has to be 2. And if the rank 2, then we project the original pencil A minus lambda B by this n by 2 matrix. And when you do the projection, you will see the top corner going to be 0, because that will be x hat hr hat equals 0. And now this is a 2 by 2 matrix, symmetric Hermitian, with a diagonal entry 0. One of the entries 0, and one of off diagonal entries not 0. Such a matrix is indefinite. All right? You can prove it indefinite using, I'll leave that exercise. So every symmetrical matrix, if the off diagonal entry not 0, one of the diagonal entry is 0, that matrix must be indefinite. Has one of the eigenvalue going to be negative. Okay. All right. So let's mu be the smaller eigenvalue of this project matrix. Then mu must less than lambda hat, because otherwise A minus lambda hat B hat has to be semi-positive definite at least. So this we know mu is less than that. Then later we're going to project every using the matrix A minus lambda B by the approximation sequence XL RL. So project. So this gives you a sequence of a 2 by 2 matrix pencil, and using mu L plus 1 to be the smaller eigenvalue of that pencil, then we have look at the 2 points. First, the subsequence of AL hat going to convert to A hat, okay? Because X, the subsequence of X and subsequence of R converge. So you're going to have this, and similarly have a B sequence converge hat. Now we know eigenvalue are continuous, right? This is a regular pencil. Therefore, this smaller eigenvalue mu L plus 1 going to converge to the mu of that eigenvalue. Okay, that's the first point. Second point, because we are picking the every step the approximation row is the best possible in that each step approximation, and that space is bigger than XLRL span the space. In the SD case is the same, but extended SD case, the space is much bigger than the space spanned by XLRL. Therefore, this best approximation row gonna be smaller than that, because one is searching the space of dimension 2, you might search in the space bigger. So you have that. Then you take a limit, and the row gonna converge to lambda hat as the first point there. And then taking a limit, then you have lambda hat equal to limit of row, that less than limit of mu, and which is mu. You end up with lambda hat is less than equal to mu, which is not possible, because previously we say mu going to be less than a lambda hat. So you have a contradiction. Therefore, the assumption is not right. R equals 0. So the proof is a simple argument. Okay, so-called global convergence. So now we're sure they're converging. And we mentioned this for convergence speed. So this is so it's converge, but we don't know how fast it converge. And to look at how fast it converges, then we introduce Chebyshev polynomial. So we talk about that. Let me skip this. We saw that before. This is one typical use. We mentioned that last week too. And this is a theorem we mentioned last time. I didn't prove, and this is one of our key theorem in the area of steep descent and kind of method. So I would like to go through the proof because it's such an important theorem. Let's look at so suppose lambda 1 is simple. If we now maybe we should refresh our memory the notation that I used. So we start with a minus lambda b, and b is definite, right? Definite. And here's the notation we introduced. Such a matrix pencil eigenvalue always real. So we order the eigenvalue from the smallest to largest. Okay, that's the eigenvalue, and each eigenvalue corresponding to eigenvector. That's the eigenvalue. Eigenvector. U1 up to UN. We further assume that we can always make that happen. Since UI are B orthogonal. Okay, which means I equal j equal to 1, I not equal j equal 0. And consequently, if we put all the eigenvector into a matrix, and this is going to be true, is a diagonal matrix, so we call lambda, which simply the eigenvalue on the diagonal, and U transpose B, U equal to identity. Okay, this is a notation we're going to stick from beginning to finish. So, all right. So we assume the first two eigenvalues are not equal, and whenever at a certain point the approximation is between the two, already between two. In that case, we're sure there's a row going to go to lambda 1 because the row getting down. The theorem says, the previous theorem says the row going to converge, going down converge to something. It has to be lambda 1. There's no other eigenvalue in between. And this omega is the eigenvalue of A minus rho LB. So given rho L, A minus rho LB is a matrix, is a Hermitian matrix, n by n, whose eigenvalue also real, and we list them from small to large. And because this rho L is between lambda 1 and lambda 2, this omega 1 has to be negative. Okay, because A minus rho LB going to be indefinite. So with those, and then the V1 is the eigenvector of this A minus rho LB, and corresponding to the first eigenvalue. This says then the estimate would be the next approximation, which is always bigger. So lambda 1 here. You have rho L. The next approximation is going to be rho L plus 1 right here because it's going to go down. And the rho L plus 1 minus lambda 1 is less than equal to the difference of rho L minus lambda 1 times a small number we call epsilon m squared. And plus something right there. And let's look at them carefully. This delta L is some quantity. It turns out to be the high order. Okay, rho L minus lambda 1 is a second order. Then look here. This is 1.5. So it's also suppose in the asymptotic sense, when your root L is almost lambda 1, and this is higher order than the linear order, so supposed to be much tinier. Even so, is multiplied by the epsilon m. Okay, so the rest is the high order, and basically what we look at that is this first two term take control. So each step you make a progress by reducing the error by a factor epsilon m squared. What is epsilon m? Epsilon m is that's why the typical Chapter polynomial comes in. It is a polynomial approximation. So you have omega 1 right here. One of the situations we talk about omega 2, omega n. So it's a polynomial that taking value 1 at omega 1, then taking as small as possible value at between omega 2 and omega n. Okay, and one of the situations that Chapter point comes in. Okay, and usually if the gap between omega 1 omega 2 non-trivial, then this epsilon m can be very tiny. So each step depend on the m. The bigger the m, the smaller the epsilon m, the faster the convergence, of course. Right. All right. And we talk about this implication, and let me pass that because we talked about before. So moments ago I was talking about if you ignore the higher order term, the error reduced by epsilon m squared every step. In general, if you're lucky, epsilon m equal to 0. Unlikely happen, but not entirely impossible. So then you would have a quadratic convergence. Quadratic convergence typically good enough in any of a numerical computation. When you take a numerical analysis class, come to the point for solving the root of a function, fx equals 0, Newton methods always be mentioned, which is quadratic convergence. And also they talk about high order. Usually quadratic convergence is more than enough in practice. Every time you double the digits, a few steps will be done. Then let's look at symbolically, asymptotically. When root L is almost lambda 1, A minus root LB is just about looks like A minus lambda 1B. Because then the reason we look at that is because lambda 1 is fixed. Root L is dynamic, is moving. So A minus lambda 1B's eigenvalue, one of them is 0, the rest is not 0. And so asymptotically, you can find the polynomial that take 1 as 0 and take as small as possible from number to number n. So again, you have this using Chapter of polynomial get such estimate. And then what you see is if lambda 2 minus lambda 1, which is minus gamma 2, sorry. Then gamma over gamma n is almost 1, then you have fast convergence. So what's the significance of the theorem? The significant theorem that later we're going to talk about that this epsilon m is dependent on the eigenvalue of A minus root LB, but not the eigenvalue as a matrix pencil. The implication that is maybe we can transform the original problem, A minus lambda B, the transformation should preserve the matrix, the eigenvalue of the matrix pencil, because that's what we need to find, right? Yet we want to make the eigenvalue of this A minus root LB more preferable. What do I mean by that? Well, you look at the bound. If you can make this tiny enough, it's in the ideal case, if you make omega 2 equal to omega n, then you can make epsilon equal to 0, right? That implies epsilon m going to be equal to 0 for m bigger than equal to 2. right? The reason because if it's just one point, you just linear. You take one here and pass through the point, you get the epsilon m equals 0. So that's the ideal case. So this become a very useful observation later on that try to shrink the eigenvalue of A minus rho LB to 2 points, okay, if you can. Not always possible, but you can always compromise a few points that will help. But you're not going to change the eigenvalue of the pencil, because that's the eigenvalue you try to compute. If you change that, you would be compute something else. Okay. Let's so since it's such an important theorem, I do want to get a proof. The proof has certain good points. So let's look. The key of the theorem that I call key lemma is in Golub and Ye. Paper 2002. The key point of this lemma is to relate the difference with omega 1. Okay, especially look at a special case. When you look at B equal to identity case. So you have omega 1 as the smallest eigenvalue, right? And if B is equal to identity, you are looking at A minus rho L identity. And that gives you the smallest eigenvalue going to be the lambda 1 minus rho L. So the two are the same. Okay, that's related to, that's easy to do. But when rho B is not an identity, you have this relation asymptotically. So omega 1 times something equal to lambda 1 minus rho L. That's this is big observation of this lemma later going to be put into the proof. Okay, and then you look at it, if B's identity. This number happened to be 1. So you have, as a corollary, you say omega 1 equal to lambda 1 minus rho L, then plus order 2. That's a defect of the proof, of course. It doesn't give you exactly as a special case, but it gives you something almost similar. In general, it can always bound by the difference. Okay, that depend on V1, which then U1. U1 we talked about. U1 is a notation of the eigenvector that we used for the metric pencil, the first. Okay, let's look at a quick proof. So the first is special case. If we know rho L is always bigger than or equal to lambda 1. If it equal, there's nothing to prove. Okay, if the equal omega 1 equals 0, they all equal. So no proof needed. So we're going to suppose rho L is bigger than lambda 1. Then this will be A minus rho L B is going to be indefinite. Okay, because you multiply a number bigger than smallest eigenvalue. That's going to be indefinite. And therefore, omega 1 has to be negative. All right. So you look at, by the definition, this is how omega 1 is defined. Omega 1 is the smallest eigenvalue of that matrix pencil. So we're going to move this all to one side. Okay, move the omega 1 V1 to the left. You rewrite, then you take V1 out. This is what you have. Okay, and since omega 1 is the smallest eigenvalue, this matrix is singular, yet has to be semi-positive definite. Okay, so you're going to have A minus omega 1 identity minus rho L B is semi-positive definite. What's the implication? The implication is rho L V1 is the smallest eigenvalue of that matrix pencil. Okay, so you combine that together. You put the rho L here. Rho L here is become singular. Therefore rho L is the eigenvalue of the pencil, but also smallest. Okay, so that's a conclusion. Now we look at mu1, lambda 1, u1. Well, let's look at by the definition. By the definition of v1, you can this is gonna, you look at this equation, right? You solve you multiply v1 from both sides, v1 transpose, and you get this equation. Okay, from the second equation you will get this. Okay, and then you separate them. You separate them into two parts. All right, that's easy. And then you look at then this is. Then I'm going to replace. This is a Rayleigh quotient in v1. Okay, I'm going to replace this by mean over all non-zero x. Okay, and so make the first term smaller. Okay, you minimize them, and the second term non-change. Now, so you get that. Well, the minima over x, one of the minimization principle we talk about, this Rayleigh quotient minimized over all x not 0 is the first eigenvalue of the metric pencil. So that's why lambda 1 there. So you get the first equation. And now what do you get here? You move, so if you move lambda 1 to the left to rho L minus lambda 1, okay, rho L minus lambda 1, and you're going to be bigger than equal to, so you get a left inequality. And then we'll look at the other way. Lambda 1 equal to mu1, u1, because u1 is an eigenvector we talked about. So this equation is from the metric pencil. Lambda 1 is an eigenvalue of a minus lambda b, smallest 1. So what you're going to do, so now what we do, we're going to do, you look at this equation. Look at that equation. Let me, maybe I can, my pointer has a better power, I think. Battery almost out. So you look at this expression. This expression basically cancel u1 transpose u1. That's cancel. So basically rewrite the first term. And if you look at that out, then numerator are minus rho lb, and then you add rho l. So if you simply, that's a add a term and subtract term, add term. Okay. So what we do, a minus rho lb, this is a positive number. We're going to make this small as possible. So we're going to minimize, now it's u1, we're going to minimize over all possible x. Okay, leave the rest unchanged. Now, minimize this over all possible x. Now back to the minimization principle. There will be the smallest eigenvalue of a minus rho lb, which is omega 1. So you get omega 1. And well, okay, so you get a lambda 1 bigger than or equal to omega 1 times that plus rho L. So you're gonna, so if we move lambda 1 to the right, move that to the left, we get rho L minus lambda 1 less than or equal to negative that equality. So we get rho L minus lambda 1 is bounded between these two numbers. You see omega 1, but these two ratio is different. One using V1, the other use U1. So that's the first inequality. The first inequality. So we prove that, right? Let's look at the asymptotic formula. So let's look at that. This will be used as some of our derivative information in error analysis of eigenvalues. So you look at a minus tb. That's a matrix function in T. So whose smallest eigenvalue is a function in T as well. So we're going to say that's omega 1t. It is the smallest eigenvalue of a minus tb is a function in T. For T in linear lambda 1, so we're going to look at only linear lambda 1. The omega 1, lambda 1 equal to 0 because a minus lambda 1b is a singular, is a semi-positive definite singular. So the smallest kind is 0. That's 0. Omega 1 PL, if you put the PL, rho L in, that's omega 1 we talked about in the previous slides. Okay. So we have omega 1, number 1 equals 0. It's a simple eigenvalue of that matrix because number 1 is less than number 2 by the assumption. So if you put the number 1 in here, you get the smallest eigenvalue 0, which has to be is a simple. It's not a multiple eigenvalue. And you know all the simple eigenvalues are differentiable if it depends on a parameter t. So if the matrix is analytic, in this case it is. A minus tb is linear. Of course, it's analytic. So omega 1t is a differentiable. So next we're going to look at omega t expansion using Taylor expansion, the simple idea of Taylor expansion at rho L. Okay, so Taylor expansion of omega 1 at rho L, that should be omega 1 derivative. Sorry about that. That's a typo. Would be the value and derivative and high order. All right, that's a basic calculus. So omega 1 p rho L is omega 1. Okay, that's notation we talk about. And what about the derivative? Well, the eigenvalue derivative. Let me put a factor right here. You can look at the reference book later. So if you have a matrix function, this is a matrix function at t equal to t0, you have eigenvalue. You have an eigenvalue. Say mu eigenvector, left eigenvector y, right eigenvector x. What that means is you have a y h equal to mu y h, a x equal to mu x. All right, have that, and then there is an eigenvalue lambda. There's a at has any eigenvalue. Let me call it omega t near t equal to 0, such that omega t0 equal to mu, omega t0 as a derivative equal to at t0. So the derivative is, at that point, is basically taking the derivative of the matrix function and you multiply left and right eigenvector from both sides. That's what you have here, because the derivative of a minus tb is negative b. Okay, so and that's the negative sign. Why you see the negative sign? Then we know the eigenvector is v1 from left and right, because it's a Hermitian matrix. The eigenvector are left and right are the same. So both v1. So you get that. Okay. So now we put the t equal to number 1, and that's going to be 0. So you get a 0 equal to the whole thing. Then you now you simply solve for number 1 minus rho L. That's what you get. Okay. So the proof is really not that complicated. Once you discuss this fact, you can get you can find in the Wilkinson book, a lot of books on the matrix perturbation. Okay. All right. So we need this theorem. Now we're ready to prove this. Okay, that we just solved before. Again, we're going to look at many steps. All right. So the first we have A minus rho LB. This is a Hermitian matrix. Therefore, you can do the eigendecomposition by unitary transformation. Or in the real case, it would be orthogonal, right? Unitary, that should be unitary because we're looking at the Hermitian matrices. That's one of the homework that I assigned. Then the omega would be the eigenvalue matrix, the diagonal. So that this first is a Hermitian, and the second one is look at the we're in the extended SD. We're looking at the Krylov subspace, right? KMCXL each step. Okay, C would be A minus rho LB. One of the things to describe Krylov subspace would be because it's a span by x, cx, c squared x up to c to the n minus 1 x, and you do all the possible linear combination, which is basically a polynomial of degree n minus 1 at most, polynomial of a matrix C times XL. That's a linear combination of the whole thing. All right. So let me write. So if we have FC equal to alpha 0 identity plus alpha 1 C alpha m minus 1 C m minus 1, right? And FC times x, let me drop the subscript just to make it easier. Alpha 0x plus alpha 1 cx. See, it becomes a linear combination of those vectors. Therefore, because you're looking at all possible f, and then the two are the same. So the space of all polynomial f of c times xl together give you the Krylov subspace. And then because of that, and then you look at the next approximation, which is the best possible approximation in the space through the entire space. So become mean for x in the Krylov subspace of the Rayleigh quotient. So what we do is a numerator, we minus rho LB and plus rho LB, and the plus one, we take it out, become a constant, the rho L comes out, okay? So, what we have is we basically inside the plus rho L, minus rho L plus rho L, and you plus one you take out. So here, now because x, this x is in Krylov subspace. The Krylov subspace is every vector is taking such a form. So the minimization become over all polynomial f, and such then you say x equal to f of a c times xl. That's what you're going to have, right? Okay. So become over all polynomial. That's when the polynomial comes in. All right. The chapter polynomial eventually going to come in to do the estimation. This trick is typical. It basically appear in all the convergence analysis for Krylov subspace, depending on matrix and how do you find the polynomial. So this step is key. Is standard practice. Right? So from vector to polynomial. Okay. There's a minimization. There's one polynomial is optimal. We don't know what it is, but this always exists. So we're going to say f opt is a minimized polynomial. Well, not for here. We're going to look at the remember the epsilon m, how epsilon m is defined, right? So to find optimal f here is difficult. So we're going to say f opt is a best polynomial in defining the epsilon m, which means that this f opt is taking 1 at omega 1 and take the other value as small as possible. So it exists, but we don't know what it is. We can keep it there. Well, we can claim that epsilon m is always less than 1, cannot bigger than 1. The reason is epsilon m is among all best polynomial, best possible. So if I can pick one particular polynomial so that the value at from omega 2 omega n less than 1, then epsilon m going to be better than that. So here's a one that I pick a polynomial of degree 1. Remember we talked about before, one of the cases the epsilon m is attainable. This is the case. Okay, just for m equal to 2, this ft is possible, just the best possible. So we use this to claim that epsilon m is less than 1. That's the point. All right. Number 4. So this is always true. We talk about that. That's right here. Okay. So this x h r x equals 0 always, no matter what x is. So this is what we have, and then v1 h xl has to be not equal to 0. This is because we assume rho L is between lambda 1 and lambda 2. So it'll take a little argument. I'll leave that to think about afterwards. If that's not equal to 0, and so that we can do the so basically here this is a shorthand. Suppose among all x not 0. Okay, if x is 0, you would have trouble. So but we didn't write there, but it's kind of convention. If you look at the books, some books just say mean over x, and really means over x not 0. It's a little sloppy, but people know that. So we need to know this is not 0, and now we just replace. This is the mean over f. So we're going to put a particular f with f opt there, and you're going to make this bigger. So before was equal, now it's less than equal. All right. Okay. So by this point, we put into the eigen decomposition, c equal to v omega v transpose. You plug in. Now. V is orthogonal, unitary, and if you put it there in, you can take V out and then become all the diagonal in between. Okay, right? This is one of a thing that if you put eigen decomposition, C equal to V omega V transpose, C square equal to V omega V transpose V omega V transpose, and now that's where we need a unitary of V equal identity, so it becomes V omega square V transpose, and you keep on doing that. Turns out for any power, c to the k is that become k to the omega, and V just always split out. So you put it in, you can take a V out. And that's why you have before was f opt of c, and then the v all out become a diagonal in it, omega. Okay, that's because that, and that's another common point. And the numerator, denominator that you put in c equal to v, v omega v transpose, but the V from the left f opt and V from right f opt cannot cross B. So you're going to have always B in between. Here, if everything is C, it's fine. They can always cancel and lift V from left and right to take them out. So you have V and V transpose. But if you have B in between, the V from the left f cannot pass in through B. Same thing from the right. And you end up with so-called B1 right there. B1 is V transpose BV. So because B in between, you cannot cancel them. B somehow is a block in between prevent you to simplify even further. That's the hard part, and that's where most people would be up to this point would be stopped right here. And in the Golub and Year's paper, that's where their idea comes in, that the key namer comes in, using somehow this V transpose B using the key namer eventually related to omega 1 and rho 1 minus L. That's another key point. So you have the B1 here. Most people would stop here, but they push forward and end up with a nice estimate. Okay. So now they need to estimate the numerator and denominator. A little complicated. I will just go through the key idea detail. Of course, you can always later to see which from steps. And I read through, and it is correct. So here's a vector y in the previous slides. We're going to take a y vector, so the vector y right here. So y vector, we're going to do what we're going to do. We're going to split the first entry and the rest of the entry. So you take the first entry out, because C1, E1. The rest is called y hat. You plug in, and then replace y by the sum of 2. Sum of 2. Now this is basically the multiplication. You get 4 terms. Then you combine the center term. You have 3 terms come out. That's just a little algebra. So the first term right here, E1 transpose B1 E1. That's then you consider the form of B1. That's eventually become V1 transpose V1, and key lemma comes in. So you have a 3 term. Let's call them cos1 times beta 1 squared, that whole thing. 2 cos1 times beta 2, the rest beta 2, and the last one we call beta 3. And as you can imagine, when you do gradually convergence, the cos1 will take control. The rest is going to go to 0. That's what you hope. And so the other 2 terms are going to be small. Eventually, that's going to take control. Then that's the intuition that you have to do estimate. So here's a beta 1 squared. All right. You remember what's the B1? So you get that term comes out. Beta 3 is because y hat h it only has the first term is 0, right? And then when this is a diagonal matrix, and y hat times the diagonal matrix, because y hat the first entry 0 is only going to pick up the rest n minus 1, which is from omega 2 to omega n. Omega 1 is gone. The rest of omega is actually less than 1. So you take that out, estimate, so you can get the this is epsilon m squared less than 1, and the norm of B1 is the same as norm of B2, and then the 2 norm of y hat, the rest. Beta 2 somehow. Beta 2, this is beta 2. You're using a Cauchy-Schwarz inequality. You have 2 inner product. So what are 2? The E1H B1 is a vector. Then you have another vector, right? The first vector's 2 norm is less than beta 1. So Cauchy-Schwarz inequality, CS inequality. Now it's called CSB, right? Bunyakovsky, the Russian mathematician. Okay. Now, then you also notice that sum of omega j cos c squared, this is YH omega y, that equal substitute. And so before we were doing transformation, now put it back. That gives you this. That equal to 0. And if that equals 0, you separate the first term and the rest, and you get the first term is going to be bigger than the rest. Okay, so in the end, beta 3 you can control beta 3 by this epsilon m times the rest. Okay, so that's so we need to so we're going to estimate beta 2 now beta 3. How about this is a numerator, right? moment ago was the denominator. No, this is the numerator. Before was so numerator is a lot easier. This is a diagonal. This is diagonal, right? So you're gonna plug in y is a vector that's a diagonal f squared and omega that's diagonal. There's no middle term. There's no middle term, only two term. When you separate y into the first entry and the rest, because of diagonal you have only two term. Then you look at y squared. This will be sum of all. And why that is true? That is true because the first one at omega 1 f equal to 1. Okay, the rest of the term omega 2 to omega n f squared is less than 1. Okay, is less than 1. So therefore this you make them bigger. So sum of omega j, because it's j squared, that's y at omega y, that's equals 0. Okay, so the whole what it says, the numerator is negative or 0. The numerator is negative or 0. Okay, that's important. Then the second term right here, second term is can control by omega 1 and cos 1 squared. Okay, now this is a term we need to estimate, right? So the first inequality is key. It's a little tricky when I first read it. It's confusing. Now you keep the numerator the way it is. So this is copy, the numerator copy. But denominator you actually make it bigger. The cos 1 you take absolute value. Okay, so you make a denominator bigger. Then if you make denominator bigger, the fraction would be, the whole thing usually would get smaller. But then, because the numerator is negative, if numerator negative, you make denominator bigger in absolute value. Denominator is always positive in here. You make it bigger in, then the whole value gets bigger. So otherwise, it is easy to get stuck here, but by not noticing this is negative. Okay, now then this equal thing here is by taking and by intuition that the first term in the numerator and denominator are going to be take control. So you take them out. This step take a little algebraic manipulation. Maybe take a half page. You need to sit down, work on that. Once you get that point, now you estimate using the previous beta 1, beta 2, beta 3 bounded by beta 1, beta 3, the rest, and then you eventually come to this point. All right. Okay. This is what we need. The only thing to this point you notice that omega over beta 1 squared. What is that? That turns out to be using the lemma. So we have this, and now the key now is looking at omega over beta 1 squared, and you plug in the definition of beta 1, and it turns out to be omega 1 over v1h v1 and v1h b v1. That's something that looks familiar because it's appear in the key lemma. So that's related to number 1 minus root L. Okay, so therefore you end up with you replace omega 1 over beta 1 squared by we have a whole thing here to define delta L, and the rest here is just copy. So you copy thing here, and then this is delta L in the lemma. We prove that's of order quadratic term. Then omega 1 over the beta 1b using this approximation. The lemma say this is bounded by the rho L over minus number 1 and times bounded by that. Yeah. Then the whole thing ends up with a proof. So I hope I highlight the key point, because the theorem of the proof is not trivial in the paper. And I think I should take we take a 10 minutes break. And we don't want to. Okay, so we this will be one of our theorem. I think the only theorem that I'll give a detailed proof. Is because it's very useful. Now let's come to the precondition. People talk about precondition all the time. Nowadays, when you do numerical linear algebra computation, rarely people don't mention preconditioning, because otherwise it can be very slow. So what is preconditioning? In roughly speaking, it's just that it is a concept that when you have a problem, you try to transform the problem, to modify the problem in such a way you don't change the solution, of course. Otherwise, you will be computing something different. But somehow the problem can be transformed to another one that is easier. Well, easier, what do you mean by easier? Mostly that means take less time, right? You get the solution faster. That's what I mean by easier. The predominantly, when people talk about preconditioning in numerical linear algebra, is pretty much about the linear system. So you have, you try to solve a linear system AX equal to B. How do you make it simpler? Well, the idea would be to find another matrix K is so that you multiply from the left. You can have the right too, but let's just stick to this left side preconditioner. So KAX equal KB. Then this new system clearly have the same solution. For K that's non-singular. If K is singular, you will change the solution. Especially if K is 0, you change the problem completely. So K is non-singular, then it's easier than before. Then you look at the extreme case. Extreme case, normally you can achieve that, but it's going to be helpful. It's always like that. You look at the case that how can we push as further to the extreme case, which is the simplest. In this case, if K equal to A inverse, all right, then a KA will be identity, then X, you have the solution right away. In a sense, that's the best preconditioner. Then you look at you have to do KB anyway, but KB then involving A inverse. So you basically didn't do anything. So such a preconditioner is impractical. You do basically the same as before. So there's a compromise. So we can do the extreme, Ka equal to identity. We cannot do the extreme because that's just not practical. That's the same as solving the original problem. What we can do is make Ka almost identity, such that then there are two meanings of Ka almost equal identity. One is Ka minus identity is very tiny in magnitude. The other Ka minus identity is almost a low rank metric, very low rank. Why low rank metrics is such important? That's again come to the polynomial. The polynomial eventually, the optimum polynomial. The polynomial in general term, in the real case, if we look at what we talked about before, in the often case we apply polynomial in the linear system and eigenvalue as well. So we take a polynomial, take a value 1 at one point, and try to make it as small as possible at the rest of our eigenvalue. So, and usually application that because we don't know eigenvalue, we make the polynomial as small as in the interval. But and in the case that it's hard to do theoretically, but intuitively, if you have a low rank, it means that you have just only a few points instead of a lot of points. Low rank means that you have just a few points right here. They clustered, or just a few points. Then you know, suppose you have a 5 point right here. Okay, that's happening if the low rank is restricted to 5. Then you can find the polynomial, take 1 here, take a 0 at this 5 point. What kind of polynomial like that? The polynomial of degree 5 would be suffice, right? And that's why you see one of the cases when omega 2 equal to omega n, you can find a polynomial that take 1 here, take a 0 at 1 point. So that's why you need a low rank case. A low rank case that the polynomial of degree 5 would be taking 0 at all 5 eigenvalues and 1 there. So you get the instant convergence in the linear system case. It's just that for theoretical analysis, that's the limitation of theoretical analysis, that normally we can't do that. Because you don't know how many, you end up with a finite polynomial that's smallest in the interval. Okay, it's a theoretical limitation. In practice, if you can make a low rank, you would have a instant convergence by making polynomial order higher than the number of different eigenvalues. If you have done any computation in the linear system, and one of the cases that if the matrix is identity plus low rank, and then you have a very fast convergence. All right, so that's for linear system. How about eigenvalue problem? Eigenvalue problem is not that natural. So let's say you have a minus denominator b. And let's say do one kind of a transformation. I multiply k from the left. So you have, now we have the original problem. I have the transform problem. How do you know that this one is easier than before, right? It doesn't come natural. In the linear system case, if I make it almost identity, in the extreme case identity, I get instant convergence. Now here, what is the extreme case? Is any k that I multiply to in such a there's any k multiply from left, I get the eigenvalue instantaneously. And another way is that. What is L to make this problem simpler? Well, in this case, there is a extreme case. If you take a L to be the eigenvector matrix, you multiply from both sides, one from by L, the other L transpose, then this will be identity. That will be the diagonal. Okay, in that case, there is an extreme case, but here you don't. But, of course, how do you find the eigenvector? That's something you want to compute to begin with. So put it together, there is no straightforward explanation. So what k makes the new problem easier? Same thing here, that even though there is an extreme case, taking L to be the eigenvector matrix, but that is I know. Other than that, how do you make that easier? Okay. So what in the next couple of slides, that we're going to show you two different ways to look at what do we mean by what kind of a transformation make the problem easier. Okay, so let's look at this is a typically people use. It's called Eigen problem preconditioning. First viewpoints. Let's look at the ideal case. So in the one-step search, line search, you add a point at XL, you have a direction, and you look at the best solution along that direction, which is on XL plus TP. That's a straight line in the seats of n. Okay. Then you wonder what direction P that you should use to in the extreme case to get a solution right away. Okay. Well, let's look at the following. So XL, we can expand it in the eigenvector of the problem, which is uj. So uj is span in high space. So you can do the expansion and take the first term out, alpha 1 u1, because u1 is something we are looking for. Then plus the rest that we call v. V is the rest of vector which is b orthogonal to u1. Okay, if v equal to 0, then we're done. Then you look at one of the ideal conditions would be if p equal to v, then you can always do take xl minus p, you would get rid of v, right? If you know v. Of course, you don't know v. Well, more generally, if p looks like that way, p equal to alpha u1 plus beta v. So somehow v appear as the whole in p, then you can do the linear combination of xl and p to get rid of v. Okay, v has to appear in whole. And when can you do that? Well, if these two vectors are not linearly dependent, which is using alpha 1 beta minus alpha not equal to 0. Okay. In the special case, if alpha equal to 0, then b equals beta v, and you can take the v off. And this is interesting that usually people are thinking, how do I get to the solution quicker? And then I should move the direction p, which has a larger component in the eigenvector. That's what inverse iteration does. Inverse iteration basically that, well, what direction should I take? I'll take the vector has a large, as much as the component as large as possible in the direction of the vector that we're looking. In this case, u1. But here, when you look at that, that's not necessarily true. You can take a p has no component at u1 at all, but simply in the opposite, then you can do the linear combination. That's the power of a linear combination. Okay, this is ideal cases. In practice, that the people use it all the time. So it's basically inverse iteration. That they're going to take take that that's a residual, and then you take a shift, so-called sigma, a minus sigma b and inverse times the residual, and that's basically rewrite residual into a minus root lb. So p is inverse times that matrix times xl, and usually this root l is not equal to sigma, and sigma is usually almost close to number 1. In the case of inverse iteration, that sigma is number 1, but typically we don't know that. So in the large sparse computation, so you pick sigma always number 1, and rho l usually unlucky to be the sigma. Okay, that's people usually do all the time. Does it make sense? Why this is a good one? Let's look at them. So it's reasonable that suppose we're computing sigma number 1, and it's reasonable we pick sigma almost number 1, but it's not equal to any of the number j, right? Number n, and you pick around neighborhood, so we're close to row number 1. You have the approximation, and you have the shift. That's all roughly from the neighborhood of number 1. And so using the eigen decomposition, you found that p equal to this vector, right? Okay, let me quickly say that. So you have, remember we have this. identity, right? And then you look at A minus sigma B equal to, this is going to give you B equal to A equal to. So you plug in, you get all right, and then you have similarly A minus rho L B going to be equal to U negative H. And putting together, and so you take an inverse of that, they're going to be U on the other side, because you reverse order, and lambda inverse, and U negative H become U H, and times that negative H and so put together we get this cancel, that cancel. So inside would be the diagonal lambda I minus sigma lambda I minus rho L. Okay, so then then put the decomposition right here. You discover P equals sum of mu I alpha j mu j. Alpha j is from the original expansion, and mu j is lambda j minus rho L. Okay, the other one. This is the denominator. That's rho L. Okay. So all the component is multiply. This can be think of the damping effect. Now, if lambda 1 is rho L is between lambda 1 and lambda 2, and close to lambda 1, and this gap is reasonably modest, so it's not like 10 to the minus 5 or something. There's a non-trivial gap. And one can show roughly, when you take a piece of paper, this mu j almost equal 1 for j bigger than 1. So this is a sum of n. Remember, we have this ideal direction. So this can separate into two terms. Can be two terms. Mu 1 alpha 1. U1, then plus the rest sum of j equal to 2 and mu j alpha j uj. Now, I claim that this is going to be almost equal to 1. If that's almost equal to 1, this whole thing is almost equal to v. That's close to the ideal direction. That's close to the ideal direction, okay? So if mu j is almost 1, then the rest happen to be almost equal to v. It's not exactly equal, but almost. So we're going to look at, so you're going to look at, so this, if you look at this is every number, what does that mean? So you have a lambda j right here. So lambda j minus rho L, lambda j distance, lambda j minus rho L, then lambda j minus sigma. So the two distances are almost equal if sigma and rho L is clustered into around lambda 1. This lambda j is further apart, and the ratio is almost 1. That's what it means. And here's a quick picture. The picture says if t minus that would be rho L 1.01, then sigma is 0.99, and you discover that at 1 is a small number, and when you stay away from 1, they're almost 1. Okay, it's almost 1. So, and when that happen, there's mu j almost 1 for j bigger than or equal 1, and then the direction almost like the ideal direction, and that gives you fast convergence. All right. So that's one way to look at the usual. In fact, you can put a theorem like that. I won't prove it. I already mentioned that the previous theorem will be the one that I'm going to prove in detail. This theorem says you start with XL. The first component cannot be 0 because that's U1 is trying to look at. And you do a shift. You find the shift to sigma that's not equal rho L. If the equal rho L, you're going to have a problem. And in such a way that mu1 is the smallest, or mu1 is the biggest. There's two possibilities depending on the shift. So it can only happen mu1 is the smallest or mu1 is the largest. If mu1 in between, nothing works. Then you can prove that you start with the angle. If the angle between XL and U1, which is the eigenvector looking for in the B inner product, is then multiplied by such a tiny number, then will be bounded by the angle of U1 to the Krylov subspace that we're expanding to. This is for the eigenvector. For eigenvalue, the next eigenvalue actually is going to be smaller than some tiny number. When you look at that, you know this is going to have something to do with the Cherenkov polynomial. It's a theoretical estimate. In practice, that is going to be usually worse than the actual number. And then bound times the angle between the tan of the angle between XL and U1 in B inner product. Okay, this Km is a Krylov subspace. Here's eta. Now we need to look at this eta a little bit. We know if you look at previous slide, this big delta is a subscript eta. If eta close to 1, this whole thing, the inside bracket, square bracket, is going to be almost infinity, which means 1 over that is going to be 0. The ideal case will be 0, then you get a convergence. So we need the eta to be close to 1. Then you look at this expression right here. So this expression becomes the product of 2. There are two cases. If mu1 is the smallest, mu1 is the largest. Let's look at just one of them. The other is basically the same. So look at the first case. That you have lambda n minus sigma, lambda n minus lambda 1. So the first factor will be lambda n, a distance between lambda n and minus sigma, okay, sigma, and lambda n minus lambda 1. Presumably, this is going to be close to 1. The second is lambda 2 minus lambda 1. So you have minus 2 minus lambda 1, the distance between lambda 1 and lambda 2. Then lambda 1 minus sigma, lambda 2 minus sigma. That's why you need a sigma also near lambda 1. Okay. In fact, if sigma equal, in a special case, if sigma equal to lambda 1, this eta would be 1. That would be the coincidental. Usually, it doesn't happen in practice. Okay. So that's the first explanation of using kind of inverse iteration, one step as a preconditioner. All right. So we just mentioned that. This case is just a little detail. You have to sit there, take a piece of paper, and remember that we need a requirement. Mu1 has to be smallest or largest. Okay, and then when does that happen? It turns out there are different cases, and we know rho. This rho is well, I drop the subscript. Rho is always between number 1 and number 2. And then sigma is, we'll say sigma is shifted near number 1. So sigma has several possible situations. Sigma is less than number 1. Usually people do that, take sigma less than number 1. The reason is if sigma less than number 1, if sigma less than number 1, this matrix will be positive semi-definite. This matrix is positive definite if sigma less than number 1. And why that is important? That's important because there's an inverse right here. There's an inverse right here. If A minus sigma B is a positive definite, and we have solve a linear system. That's the case. A linear system is easy to solve. So using a conjugate gradient, linear conjugate gradient for solving a linear system. So this is the first one that people use all the time. Often people use more often than the other two. Okay, because they get to the case that when you solve a linear system, become a lot easier than other case. Then your sigma has the other two possibility is between number 1 and a rho, or bigger than a rho. Then you have this is take a piece of paper and analyze when the mu1 is the smallest or largest. Okay. Okay, I just mentioned that. Why we like the first case, because you can use a conjugate gradient. The other two cases you can do using incomplete decomposition of A minus rho B and using some kind of iterative method. Sherry's talk about that, so I won't mention it. Then you can, the CG case first, if it's a other case, you can so-called mean rest. You would hear a lot from Sherry's lecture. Okay, that's the first way to look at it in preconditioner. The second way, let's look at second way using Krylov and Year's theorem. Okay, this is a theorem they have. Okay, I put copy right here, and that's a high order. We can safely ignore that. So what it says that looking at this theorem, how can we make epsilon m smaller? Okay, the best case would be 0. All right, remember this omega is those eigenvalue, right? Okay, so the idea is, so this is the original problem. I'm going to transform by L from L inverse from left, L negative h from right. In such a way, this L inverse is easy to do. L could be lower triangular in most of the case. Then L inverse is forward substitution. And so that this matrix, so remember this omega 1 is A minus rho LB's eigenvalue. Now, if we do the transformation, then apply the SD on this matrix pencil, then in the end we would depend on the eigenvalue of this matrix, all right? Okay, so in the ideal case, the eigenvalue of this matrix, you can make it, if you can make the last n minus 1 eigenvalue all equal, and then omega epsilon m going to be 0 for m bigger than or equal to 2. We talked about that. Then you have a quadratic convergence. Quadratic convergence is basically good enough for any numerical computation. Okay, pretty much. All right, how can we do that? Well, let's look at the ideal case. So suppose we do an exact decomposition, the exact LDL decomposition. L is lower triangular. Then you multiply L inverse from left, L inverse conjugate transfer from right, you get equal to D. This D is diagonal plus minus 1. So that means you have one eigenvalue negative 1, the other plus 1. So omega 2 to omega n would be plus 1. Omega 1 would be negative 1. And that would give you epsilon m equal to 0 for m bigger than or equal to 2. So that would be very, very nice. Okay, you can do that. But there are a couple of problems with that, of course. So here's the 3 things that I list here. So this decomposition might not exist, and we know that this is basically LU decomposition, right? It's not always exist. It exists. The sufficient condition would be necessary, and sufficient condition would be. Anybody know LU decomposition? The leading principal submatrix non-singular. All the leading principal submetric. So it may not exist. Okay. If it exists, it's maybe numerically unstable to solve, because remember, this lambda rho L is going to be closer and closer to lambda 1, so A minus rho LB is going to be closer and closer to singular, and when you do that decomposition, even you are lucky, all the leading principal submatrices are non-singular, and some of them may be close enough to a singular. Then you have a stability issue. There's the second. The third would be, we all know, you take as in the Sherry lecture, usually when you're solving, doing LU decomposition for large sparse matrix, and you introduce a loss of fill-in. And unless you do a certain permutation, even that, not all metrics can do a good permutation to reduce the fill-in. So that means that this L matrix is lower triangular, but maybe dense, almost dense. So when that happens, later you have to solve a linear system with L. You can make the cost as high as order n squared, which is too much, all right? So the rest computation is going to be very expensive. So there are at least 3 problems here. So what we do is always do compromise when you do a compromise, it usually work very good in practice. You see the numerical behavior is very fast convergence, but there's not a lot of theory to predict what it is, but it works well. So what we do is that you can do the decomposition, incomplete decomposition, almost equal in such a way that there's one smallest isolated eigenvalue. So omega 1 is isolated. You hopefully away from the rest, which the picture I erased, that because omega 1, omega 2, so the gap play a big role. Then you make the rest of eigenvalue, hopefully, into a cluster, tight cluster. Not ideally into one point, but maybe five clusters, close enough, or 6, 10. It's just a rough number. It's of order 1 clusters. And if you can do that, then you're fine. Your code will run very quick. So here, therefore, you do approximately equal has 2 meanings, right? Either is the approximately equal in the Euro sense, or just has a low rank. It's a low rank happens again. So this is what we do. All right. Now let's look at a couple of things that you know. LU decomposition is not cheap. From Sherry's lecture, you know that. The original, the most ambitious version will be you do LU decomposition or LDLH decomposition every steps, and that's going to be increase your speed, but increase the speed in terms of from one step to the next. But each step going to be used cost a lot of time to complete. So one idea that we can fix L, just use one L for all the iterations, and you do sometimes that may be even faster, because really the preconditioning computation is not cheap. Okay, so that's one of the idea. You fix the preconditioner using constant. How do you do that? Usually, say we compute lambda 1. You pick you can always estimate lambda 1 where the range is. That's not hard using Lanczos or any iterative method. And so you pick a sigma is almost equal to lambda 1. in the small range. Then you do a one LDL decomposition, and then you can actually estimate in the middle that the C matrix, I should take the head out. There really shouldn't be a head there. Then in the middle for row L, you can write this equation out. So as long this could be almost identity D if sigma and rho is pretty much the same. This is just a rough give you idea, and then this L still be a good preconditioner. All right, so what's the second idea? Second idea would be you transform the original problem by L and apply SD or extend SD. So which means every step you're going to solve a different problem, and this is the so far. Now there's an alternative way to. This is typically the case that you have a problem, transform, you do an algorithm on it, and then you can somehow do that on a piece of paper to reform the problem, and so that the whole thing run in the same format. This happened the same again. So let's see. So we're going to talk about implementation. Instead of apply ESD on this problem, on different problem every step, we could do a different implementation. So let's see. We have this original problem. This is a new problem. Okay, this is a new problem. The typical step would be if we're going to apply to symbolically apply to the transform problem, it's going to look like this. We're going to compute the smallest eigenvalue mu and a corresponding eigenvector of this matrix, okay, that matrix, with everyone with a hat, okay? That means the transform problem. So here's the notation that you have a hat or new hat. New hat is for the original problem. With a hat is for the same notation for the transform problem. So we're looking for this, solving this eigenvalue problem. This Z hat will be the Krylov subspace of that. Z hat will be the basis metric of that Krylov subspace. Everything with a hat. Now let's look at this. Each vector in the Krylov subspace with a hat would be this vector. Okay, L hat minus rho L hat, right? Then you look at the relation between hat and new hat. In terms of A, you plug that in, and you take L out, okay? See, if you apply inverse here in this HL going to be canceled, okay? And then this is the Krylov subspace with hat, multiply L, capital L inverse conjugate transpose, and become the Krylov subspace of something without hat. Of course, rho L is a hat. Rho L is a scalar. Later we find rho L hat is the same as rho L, doesn't change. All right. So the XL is XL hat is such a relation, and KL turns out to be the capital L and capital L transpose multiplied together, take an inverse. Okay. Z and Z hat has such a relation, and then you look at the projection with the hat. All right, it turns out the same without hat. Okay, and the rho L hat the same as that. So now we can remove the hat completely, new hat. And so this step is equivalent to this: compute the smallest eigenvalue mu and corresponding eigenvector V of the projection matrix of the original matrix, where only Z now is a basis matrix of the Krylov subspace, and only thing that there's a KL here to be a preconditioner. You can take KL to be constant for constant preconditioner. All right. So to summarize, you end up with a preconditioned steepest descent extended. So what happened here is you construct a preconditioner KL that can be different from L. This is for generality purpose. Or you can keep K with independent of L, and you compute the basis of Krylov subspace. How do you do that? You can use Arnoldi, we'll mention later. And the whole framework the same as before. Only thing changed is here you have to create a preconditioner and compute the basis of so-called preconditioner Krylov subspace. And the way we formulate it here, it does not include both kind of preconditioner we mentioned. We have two ways to look at preconditioner 1 and 2, and now by reformulating the second preconditioner idea, then the two somehow merge into one. All right. Because of the way we derived, you will have this theorem, basically copy. Only thing is now this omega will be the eigenvalue of KL, the preconditioned matrices. Before was without K, so before omega will be the eigenvalue A minus rho LB. Now is the eigenvalue of multiply KL to make the eigenvalue distribution more preferable. By that we means make epsilon m is smaller. Then you have to change this a little bit, but that's fine. Those are the high order term, all right? There's a difference here. Before there's no KL, now there's the inverse. But the key part will be the first term, that epsilon m will be defined using the eigenvalue of the preconditioned matrices. Fast convergence. Okay, this is a discussion we talked about before. We have here, just for a refresher of memory, I'm going to skip that because we talked about that before. And I do want to mention this last case that rho L equal lambda 1. And when asymptotically, this is going to be the dependent eigenvalue of that matrix. Okay, let me look at this next theorem is a very early one called Cauchy theorem. Basically, accomplish the same goal. Only thing is this is just for SD. Achieve the same purpose basically. That compared to Golub and Year's result would be this is strict bound. It's not, there's no order n squared in the end. Then looks a little bit more complicated. Let's just look at what it means. This is only for m equal 2, which means steepest descent. You eigenvalue of KL A minus lambda 1b. So this is a fixed. Previously we were asymptotic. We put lambda 1 there too. So eigenvalue is going to be gamma 1. The first is going to be 0. The rest is positive. Lambda 1 is simple. We're going to assume that. Rho L is already between lambda 1 and lambda 2. You define a delta. This delta is supposed to be a small number as the computation progress, because there you have a rho L minus lambda 1, and this tau will be 2 over gamma 2 plus gamma n. The condition is, suppose this is less than 1. Asymptotically, this is going to be true, okay? Sufficient close. Then rho L plus 1 minus rho L times something squared times the previous error. Now, we have to look at this carefully. This epsilon 2 is the same as before. This expression is a little bit more complicated, but let's look at the following way. When you get closer enough suppose delta is sufficient tiny, almost 0, this everything inside the bracket is almost epsilon 2. It's basically asymptotically, because this is 0, almost 0. That's almost the denominator almost 1. So this gives you the same thing. You give the same thing for epsilon 2. The proof that I list here, but I don't plan to go through. The proof has several key points. I want to mention that the nice idea of a proof that may be useful in the future when you do some convergent analysis, that is using so-called semi-norm. Semi-norm means that you have a matrix right there that is semi-definite, okay? And is the using semi-norm A minus denominator B is nicely that as an error comes out, okay? That's a beautiful theory by Samaguchi. The original paper of Samaguchi was not for generalized eigenvalue, but the proof is carried over without much change. If B is not identity, as what here, the proof is simply the modification of what Samaguchi is for B is identity. And the key part, as I mentioned, is so-called semi-norm. And this equation, you might not appreciate at this point, but as you look at this proof more carefully, you would appreciate this equation very much. That is that using the matrix A minus denominator and B as a semi-norm, somehow for any vector here, the error, which is rho W, which as a Rayleigh quotient, minus denominator 1 appears. So by using the semi-norm, the error term nicely comes out from the norm error. So I wanted to Okay. Well, a couple of slides will be done. Deflation, because the other day I showed you the stupid sand code. I do deflation. I mentioned 2 deflation ideas here, but the one we're going to use through shift. One of the ideas by orthogonalization. I'll leave that for you to read yourself. I'm going to emphasize the shift deflation because that's what happened in the code that I showed you the other day. And the shift being used this deflation has been used in every code that I put on the web if you have time to look at it. So it's based on the one of the homework the assignment that you have work on. So here, let's say we assume we already compute the first k, already have approximation of the first k eigenvalue. What do we mean by already know? So we symbolically put them into a diagonal matrix called D, bold face D, hold the eigenvalue denominator I, U, bold face U, hold the eigenvectors, and assume those you already know eigenvector are B of normalized. All right. I'm going to just skip that. You can read afterwards. I'm going to talk about this shifting deflation. This is a theorem that in the homework that you have complete that says if you using U1, which is the first k eigenvector, exact eigenvector, and you consider this matrix pencil and the original pencil, they share the same eigenvector, but the eigenvalue of the new pencil, shifted one, it's going to be different. The first k eigenvalue is shifted by a number called zeta here, which is a shifted put right there. And then the rest eigenvalue doesn't change. The idea here would be that you somehow, if you know first k, you pick a shift zeta big enough so that lambda 1 up to lambda k plus zeta is bigger than the next eigenvalue you're interested. So you still, when you do that, you're still going to be computed the smallest eigenvalue of that pencil, okay? And make things easy, okay? But as I said, this k plus 2, we don't know. Somehow we can estimate, you pick a number sufficient large, and that will do. And so I think I'll stop here.